Hi everyone, my name is Praveen. Today I'm going to give presentation on the simulation model for the PN junction based on SOI. Then first we'll get into the what is PN junction and what is simulation and overview of SOI. So the PN junction is formed by joining p-type and n-type semiconductors which are doped to create an excess of holes and electrons. At the junction, electrons from the n-type material and holes from the p-type material diffuse into each other, recombining and creating a depletion region. This region acts as a barrier that blocks current flow, allowing electricity to pass primarily in one direction. So enabling the junction to act as a diode, this behavior of this junction under various electric fields is fundamental in many electronic devices affecting their functionality and efficiency. So this is the introduction of the PN junction. Then how the simulating a PN junction involve using specialized software to model and analyze the behavior of the junction under various conditions. So this includes studying the formation of the depletion region, charge carrier dynamics, and the electrical characteristics such as current voltage relationships. So here we use the simulation tools like the TCAT, like technology computer aided design, in visualizing the movement of carriers and the effects of doping, voltage, and the temperature on the junction properties. And next, the overview of the SOI technology. Here, SOI is the silicon on the insulator. Silicon on insulator technology is like an advanced semiconductor fabrication process that enhances device performance and reduces power consumptions by incorporating a thin layer of insulating material beneath the active silicon layer. SOA allows for improved isolation, reduced parasitic capacitance, and better control of short channel effects in transistors. This buried insulator, typically made of silicon dioxide, provides electrical isolation between the active device layer and the underlying silicon substrate. This unique structure enables faster switching speeds, lower leakage currents, and higher radiation tolerance compared to the traditional bulk silicons. Now we'll jump into the like how simulation model for the PN junction works based on the SOI. Here first we need to build model building. So actually, as we discussed, SOI is like a rapidly becoming mainstream commercial technology due to its lower power, higher speed, and higher packing density. So SOI technology offers performance advantages over bulk silicon technology for single event upset hardness and dose rate hardness. The response of SOI device during total dose radiations is more severe than the bulk silicon device for the existing of the box. So the shallow junction is used to solve this problem by avoiding the back channel absolutely. And this also results in special PN junction. If the negative bias of the PN junction is large enough, the depletion region may touch the box, which depends on the depth and dose of the shallow junction. This is very different from the PN junction in bulk assay. So here we'll present a simulation model for this PN junction, and then we'll verify the model based on the measured data. So the PN junction was fabricated using PDSY process. Here you can see the two figures. Like for the first one is the simplified layout of the PN junction, and the second one is the cross-sectional view of PN junction. So unlike the common process, the diffusion of the N plus doesn't touch the buried oxide in this process. So there's like a PN junction between the N plus and the P well at the bottom of the N plus and the lateral of N plus. This junction is differs from the junction in the common SOI process, and it is also different from the junction in the bulk SI process for the reason that depletion region of the PN junction may touch the box before it reaches the maximum depletion layer width, and then influence of the CV character of the PN junction. In this slide, we figured it's the measured CV character of the PN junction. It is shown that the curve is not smooth like the normal diode, and it can be divided into three parts according to the working conditions. Part A, Part B, and Part C. Based on the measured data and the theory analysis, it is assumed that the bottom junction and the lateral junction all work in the Part A. Only the lateral junction work in the Part C, and Part B is the transition region. The bottom depletion region first touches the box at point X, and the capacitance of the bottom junction decreases from point X to point to Y. Actually, this model is established based on the assumptions and is implemented in the Verilog A based on the standard diode model. Here you can see the code is divided into three parts according to the bias of the PN junction. Here you can see the most important code is like where the parameter VD is the voltage bias of the PN junction. The parameter area and PJ are the area and perimeter of the junction. The parameter CJO is the unit area junction capacitance, and the parameter CJSW is the unit length junction capacitance. So the parameters V1 is the voltage at point X and parameter V2 is the voltage at point Y. The charge in part B is assumed to quadratic function of Vd. For the reason the capacitance curve is nearly linear in part B. The parameters A and B can be calculated based on the continuity of the capacitance. This model based on the physical mechanism and the parameters are easy to be extracted. Then we can see how this model can be verified. Here we extracted the parameters of the N plus P junction with the model build program developed by Keysight Technologies. Here you can see the simulated and measured CV character of the PN junction. This model can fit the measured data well, especially in the transition region. This junction model can also be embedded into the MOSFET model, and we have also used a ring oscillator to verify this model. Here a 10-1 stage ring oscillator is used as the validate circuit. This schematic circuit you can find it here. The width of the PMOS for the inverter is 40 UM and the width of the NMOS is 20 UM. We have measured and simulated the period of the ring oscillator, and the results are shown in this table. Actually, this is the simulation model for the PN junction based on SOI process is proposed based on the PD SOI process. Here you can see the bottom PN junction and lateral PN junctions are and the conclusion is like a considered in this model, and the additional influence of the voltage bias of the junction to capacitance is also considered in this model. Then this model is actually we have verified by the junction itself by the ring oscillator. And also future considerations, also ongoing research should explore the advanced materials, novel device structures, and improved numerical models to enhance the accuracy and prediction capabilities of the PN junction simulation and SOI platforms. And there are also emerging trends as the technology continues to evolve. Integrating the PN junction simulation with machine learning and optimization algorithms could lead to breakthrough in device design and performance optimization. And experimental validation. Validating the simulation results through comprehensive experiment studies will be crucial to ensure the model's reliability and guide future development in SOI based PN junction technology. That's it. Thank you everyone.